In this video, we're going to be discussing the introduction to decimals. Pretty much this is one of the many videos that we'll talk about that deals with decimals and rational numbers and percent. In this video, we'll talk about just the introduction of decimals, and we're going to look at how to represent decimals and order terminating decimals. Now, the word decimal comes from the Latin word decim, and it means the word 10. So the decimal number system has as its base the number 10, and it's usually the base 10 system. Now we can represent the number 12.61873 as follows. And this is how we represent that number. And it's called expanded notation. Here the 1 is going to be in the tens place, so that's 1 times 10. The 2 is in the ones place, so that's 2 times 1. Now the decimal point means that any number that's after the decimal point, that's a fractional part of the power of 10. The 6 is in the tenths place, so that's 6 over 10 to the first power. The 1 is in the hundredths place, that's 1 over 10 to the second. The 8 is in the thousandths place, that's 8 over 10 to the third. The 4 is in the 10,000ths place, as be 4 over 10 to the fourth. And the 3 is in the 100,000ths place, which is 3 over 10 to the 5. Now, the correct way of reading this number is going to be this: 12 and, the decimal point represents the word and then you'll read the number, and then you'll give that number the name of the very last place value position of the very last number. In this case, 61,843 hundred thousandths, because the last number is a 3 and it's in the 100,000ths place. So you give that number after the decimal point the name of the last place value position of the last digit. And this is what the place value chart looks like. Each place of a decimal may be named by its power of 10. Okay? Now this place value goes on and on and on to the right, just like the place value on the left of the decimal point goes on to the left. Okay? And the decimal point represents the word and. The first number after the decimal point is the tenths place. The second number after the decimal point is the hundredths place. The third number after the decimal point is the thousands, then 10,000s, 100,000s, then it goes on to millions, 10 millions, 100 millions, billions, and so on. Decimals can be represented using concrete materials like the base 10 blocks that we talked about when we were dealing with whole numbers here. We can let a long in the base 10 block represents 1 unit instead of letting the cube represent 1 unit, which means that the cube right here will have to represent 1/10, and we let no long represent a single unit. So if we want to represent 5.4, we'll have 5 longs for the 5, and then these unit cubes represent 1/10. So 4 unit cubes for 5.4. Or 54 cubes will represent 54 tenths. Okay. We can represent a decimal such as 2.235. We can think of a block as a unit. Okay. So here, for 2.235, the 2, we're going to let the block represent the number 2. Well, 2 blocks represent the number 2, and then the 2 flats represent the 2 tenths, the 3 longs represent the 3 hundredths, and the 5 unit cubes represent 5 thousandths. So not only the base 10 blocks can be used to represent whole numbers, it can also be used as a concrete representation of decimals. And here's some examples here. We want to convert each of the following to decimals, like 25 tenths. Okay. I can break up 25 as 2 times 10 plus 5, because 2 times 10 is 20 plus 5 would give me 25. Then I can rewrite this as 2 times 10 over 10 plus 5 over 10. Now these 10s divide out, I'll be left with 2 plus the 5 tenths. Now 5 tenths can be written as 0.5. So 2 plus the 0.5 would be 2.5. That's how we convert a fraction into a decimal. 56 over 100 would be 0.56. Because if you look at the number 100 in the denominator, there are 2 zeros. So that means there must be 2 numbers in front, behind the decimal point, and the 5 and the 6 will fit. Now for the 205 over 10,000, there are 4 zeros in the number 10,000. So that means there must be 4 digits behind the decimal point. Okay? And the way we do that, we have to work backwards by placing the 5, the 0, and the 2 like this, and I'll show you the representation. There are 4 numbers behind the decimal point. For 205, we have to put the 5, then the 0, then the 2, and we have to put a 0 as a placeholder in front of it. Because in this case here, there are 4 zeros, so that means in the 10,000ths place, you must have 4 numbers behind the decimal point. Okay. Now for this one, 7 over 2 to the 6th power. Now the way they did this, they rewrote this in a way so that we can have a power of 10 in the denominator. In this case here, I know that to get a power of 10, I'm going to have to multiply by 5. Since I got 2 to the 6th, I need to multiply the numerator and the denominator by 5 to the 6th power, because I want these exponents to be the same. And when I do that, the denominator, 2 to the 6th times 5 to the 6th, another way of writing it would be 2 times 5 raised to the 6th. And then 5 to the 6th power, if you simplify that, it would be 15,625. And then that's multiplied by 7 to give you 109,375. Over, now 2 times 5 would give me the 10. So it'll be 10 to the 6th power. And 10 to the 6th power is 1 million. Or 1 millionth in the denominator. So that means in our decimal, we need 6 numbers behind the decimal point. And the 5 would be in the last place value position, and then we just fill in the numbers as we go along. Since we have 6 numbers in 109,375, all 6 numbers will be filled in that place. So that means this will read as 0.109375, or 109,375 millionths. And then part B, 1 over 2 to the 3rd times 5 to the 4th. Well, we got the 2 and the 5. But what we want to do here is make the exponent for 2 the same as the exponent for 5. The exponent for 5 is 4. So to make 2 to the 3rd, 2 to the 4th, I need to multiply the numerator and the denominator by 2 to the 1. So in the numerator, 1 times 2 would give me 2. 2 to the 3rd times 2 to the 1 would give me 2 to the 4th. If you recall, when you multiply powers of the same base, you always add your exponents for that base, and then bring over 5 to the 4th. Now 2 to the 4th times 5 to the 4th can be rewritten as 2 times 5, all raised to the 4th. But 2 times 5, of course, is 10, so that would be 10 to the 4th power, or 10 thousandths, which means there must be 4 numbers after the decimal point. The 2 will have to take the last decimal place, because it says 10 thousandths. The other numbers will have to be zeros in front of the 2. So it'll be 0.0002, or 2 10 thousandths. Okay, another example, 1 over 125. Now to rewrite 1 over 125, that's 5 to the third power, because 5 times 5 would give me 125. But I want a power of 10 in the denominator. Well, I know 5 times 2 will be 10, but if I want this to be 10 to the third, I need to multiply the numerator and the denominator by 2 to the third power. And 2 to the third will give me 8. And then 5 to the third times 2 to the third would be 5 times 2. All that's raised to the third power. 5 times 2 is 10. So that'd be 10 to the third power. So I have 8 over 10 to the third power, or 8 1,000ths. Meaning I need 3 numbers after the decimal point, because this last decimal place value position is the thousands place. The 8 can go there, but the other 2, I need to put zeros there. So it end up being 0.008. Part D, 7 and 2/50ths. If we write 2/50ths as a prime factorization, you'll have 2 times 5 to the third power. Well, I got the 2 and the 5, but I need to make 2 to the third. So I need to multiply the numerator and the denominator by 2 to the second. Okay? Now, 2 times 2 to the second would give me 2 to the third. And then that can be rewritten, and then multiply that by 5 to the third. That can be rewritten as 2 times 5 raised to the third. 2 to the second is 4. 4 times 7 would give me 28 in the numerator. And then 2 times 5 will give me the 10. And that would be to the third power. So I have 28 over 10 to the third, or 28 1,000ths. But I need 3 decimal places for that. The 8 can go in the last place value position. The 1 in front of it, the 2 would go in front of that, but I need to put a 0 there, right after the decimal point. So it'll be 0.028, which will give me the correct number for 28 thousandths. All right, let's talk about terminating decimals. The ones that we just did were all terminating decimals. Decimals that can be written with only a finite number of places to the right of the decimal point are called terminating decimals. A rational number, a over b in simplest form, can be written as a terminating decimal if and only if the prime factorization of the denominator contains no primes other than 2 or 5. That's very important. If the prime factorization of that denominator contains no primes other than 2 or 5, that fraction or that rational number can be written as a terminating decimal. Take a look at these examples here. The ones on the left can be written as terminating decimals, 7/16. Because if we rewrite 16 as 2 to the 4th power, we have no other primes other than 2 and 5. 19/40 is a terminating decimal because 40 can be written as 2 to the 3rd times 5. Again, this has no primes other than the number 2 and the number 5. Same thing for 3 over 160. That too is that can be written as a terminating decimal because 1/60th, 3 over 160 is 2 to the 5th times 5. Again, there are no prime factors other than 2 and 5. The one on the right cannot be written as terminating decimals, like 11/18, because 18 is 2 times 3 to the second. It has 3 as a prime factor, because we can't have primes other than the number 2 and 5. The same with 5 over 26. 26 is written as 2 times 13. Again, we cannot have prime factors other than 2 and 5. The same with 9 over 84. 84 is broken up as 2 to the second times 3 times 7. Okay, so keep in mind, terminating decimals are exists when the denominator has no prime factors other than the number 2 and 5. Now we can order terminating decimals from least to greatest or from greatest to least. A terminating decimal is easily located on a number line because it can be represented as a rational number a over b, where b is not equal to 0 and b is a power of 10, like 0.56. Okay. Here in this case here, 0.56 as a rational number would be 56 over 100, which is bigger than 50 over 100, or 5/10, but less than 60 over 100, or 6 over 10. Now, to compare terminating decimals, it only takes 3 steps. Like in this case here, if we want to compare 0.67643 and 0.6759, what you'll do is line up the numbers by place value. As you can see here, these two decimals are lined up by place value. You'll start at the left and find the first place where the face values are different. Well, in this case here, in the ones place, the zeros are the same. In the tens place, the sixes are the same. In the hundreds place, the sevens are the same. But then when you go to the thousands place, their face values are different. You have a 6 and a 5. Then you're going to compare those digits. The number containing the greater face value in this place is the greater of the two numbers. And as you can see here, the digit in the thousands place are different. Here 6 is greater than 5, so 0.67643 is greater than 0.6759. So this is how you would compare terminating decimals. Just line up your numbers by place value, and then start comparing each place value position until you get to the place value position where the face values are different. Alright, so that would conclude this particular section on the introduction of decimals.